This tutorial covers spectral products. These spectral products can be used for vegetation, water, and urbanization studies. So we'll start by walking through the notebook, which has already been run a single time, and looking at the various components of the notebook. As with all of the notebooks, they start off with importing the data cube configuration, loading in some code for libraries, and then the data cube API. The next thing we do, anytime you see in the code where it says change here, in this particular case, this is where the user has the ability to change some of the core code and to make the case run for themselves with their own data. So in this particular case, we can change the cube that we use. Here we chose Landsat 8 over Kenya. You can choose any one of the listed countries in Africa. The next thing it does is it gives us the latitude and longitude extents of the cube and the time extents. You can see here for Landsat 8 that it goes from April 12th, 2013 through December of 2017. Here's another area where you can change the code content. This is an area where you define your analysis region. So the case we're running here is over Mombasa, Kenya, along the coast. This is the latitude and longitude extent, the minimum and maximum. And if you wanted to run a different one, you could remove the comment statements. All comment statements are these hashtags. If there's no comment statement, it's going to be run as core code. This plots the analysis region, so you can see the bounding box here with the coast along the coast of Kenya, Mombasa. This is where we load the data set into memory. That loads all of the data into the memory for our latitude and longitude and time extents. So it takes the larger Kenya cube and pulls out the pixels that we need and stores it into memory. This is just a validation of the data that we have. So we spit out the Landsat data set. It shows us that we have 738 pixels in latitude, 743 in longitude, and 19 time slices. And in this particular case, we go further on with masking clouds and cloud shadows, and we do a combination of things here. We create a data set that is land and water, and then we create a different data set that is land only, because that might give us different spectral products. Here's another area that we can change. In this area is where we choose the compositing method. So I want you to think as compositing as the ability to filter out clouds using a variety of different algorithms. The most common ones we use are a median mosaic, which is the midpoint of the spectral information in the time series. A median is a spectrally consistent median, so it's a bit better than the median, but it's also more computationally intensive. And then this one is maximum NDVI, which is the maximum vegetation or the maximum greenness at any point during the time period. So now let's go down and look at some of the products. The first one that is put out is an RGB, which is a red, green, blue natural color image of the land and water composite. So you can see both land and water. This next one is an RGB of just the land. So what it has done is it has removed all of the water pixels and colored them black so that they're not included in the analysis. And as you can see here, all the water is gone, not included. This is fractional cover. This is an algorithm that was written by CSIRO Australia, Juan Gershman. You can go look up that online and find out more information. It's a really excellent algorithm, but it's a spectral unmixing algorithm that looks at all the bands of Landsat and iterates between the combination of things that are bare soil, which show up as red, blue is non-green vegetation, and then of course the green tends to be dark vegetation. It really is an interesting complexity of colors and information, but what you get at is you can see urban areas often show up as red because they mimic the bare soil. You can see areas of dense dark vegetation in the dark green, and then areas of lower vegetation and grasslands. Really an excellent product. Now let's look at some other land spectral indices. The code here defines a number of other common spectral indices. These are the normalized difference buildup index, which is for urbanization, normalized difference vegetation index, a water index, soil adjusted vegetation index, and enhanced vegetation index. These are the equations, and you can kind of see how they use various combinations of bands. These are how the equations are applied. And then let's look at some of the products. The first one is an RGB that takes the buildup index for the red channel, vegetation for the green, water index for the blue channel. There's your product here. Things that are blue and purple are water. Things that are closer to bare soil or urban areas are going to be darker red. And then, of course, vegetation shows up in brighter green. And as you can see, it's quite similar to what you get for the fractional cover, but not quite as detailed and not quite as good. The fractional cover tends to give a better representation. Let's look at a few others. This is the buildup index in just a single color, red. The scale here is -1 to 1. Darker areas are going to be more buildup and more urbanization. NDVI, vegetation. Dark green vegetation, so this is very dense dark vegetation. Things that are in low vegetation are going to be lighter in color. Here is a custom color map that was added to NDVI. Since NDVI tends to be one of the more popular output products, we applied this custom color map, which colors anything between -1 and 0 as blue, which is typically water. Urban areas or bare soil are in the low NDVI range. Then low amounts of vegetation are 0.1 to 0.4. Croplands are in the middle area, and dense vegetation is dark. So this is a custom color index. You can actually change these values if you want and build your own custom index. And what you see is a much more interesting plot of NDVI that really does a nice job of pulling out the urban areas here. It pulls out the water very bright, the dense vegetation, the medium vegetation, and things that are light vegetation. So these are some things that you can do by adjusting the output to your liking, creating your own color map. Here's the enhanced vegetation index, which is similar to NDVI, but slightly different. I like this one a little better because the scaling -1 to 2.5 and has a bit more depth of information. This is the soil adjusted vegetation index. This is the water index, NDWI. This is water observation from space, which is WAFS. Anything that is 1 is water, 0 is non-water. Since this is a mosaic, it's a single point in time. All we want to know is precisely where the water sits. And as you can see, there's some outcroppings here of water along those edges. Very interesting. It's probably a water vegetation mix there. And then finally at the end is where we get into creating threshold plots. This is the area code that gets a bit more complex, but what we do is we take some of the index plots that were created in the prior part of the code and we sift out and put a threshold range for the data, and we can create a mask and actually count the number of pixels that fall within a given threshold. It's really good for finding areas of dense vegetation or finding areas of urbanization, and so I'll show you some of those examples. So this is an area where we can change. Again, change here. This is how you choose the various threshold ranges. So if I'm going to do NDBI, vegetation index, EVI, or fractional cover, I have to choose one of them here. In this case, we've chosen fractional cover, and what we've done is created a minimum threshold of 40 to a maximum threshold of 100, because fractional cover goes 0 to 100, where some of the other indices go -1 to 1 and so forth. And then I apply that to the threshold plot of fractional bare soil, and this is the result. So if we go back and we look at the fractional cover plot at the top, we'll go back where we were. Here's the fractional cover plot. And what I'm doing is I'm sifting out all of the areas that had high bare soil response, which is typical of urbanization, which are these areas in here. So it tends to look like bare soil. In areas that we know are not bare soil, urbanization has a response similar to that. And what you'll see is an area that looks very similar to what's happening with the urban areas, but you also pick up the true bare soil, which is these areas along here on the riverbanks as well. So it's not perfect, but it does a really nice job. You can change that to look at vegetation indexes, and we'll do that in a moment. If you go a little further in the code, you'll see where there's some threshold counting, and you also have to change here and be consistent. If up above I was calculating fractional cover, down here I want to remove the comments under either threshold count or threshold percentage. And what this does is it gives me the percent inside the threshold. It's saying that in that figure, 10.9% of the pixels fall within the range that I specified. Finally, at the end, we have some water counts. So if I want to know what's happening with water, I can change it to a threshold count or threshold percentage to count the number of water pixels in the scene. I can do the same for the WOFs, water observation from space. Since that number is only 1.0 for water, we just create a fictitious threshold 0.9 to 1.1, which means 1's in the middle, and I can find the percent of water. And so we can compare those two things. So at the very end, there's a GeoTIFF output. If I just want to output the GeoTIFF product of my composite, this is where I do that, and I can pull in the bands that I want in my land and water composite. I can pull that into my favorite GIS tool. So finally, we're going to change a few things to show you how to modify the threshold parameters. So I've gone back here to the NDVI plot. This is the NDVI plot where I use this custom color map. And what I'm going to do is I'm going to modify my algorithm for calculating the threshold parameters, and I'm going to look for all of the croplands that are either light green in color that you see here or dark green in color. So everything from 0.4 to 1.0, all of these green areas, I'm going to count up the percent within that picture that is green. And this is an interesting way to compare two different time periods. I might run an analysis for 2015. I might run an analysis for 2017. I know that there's vegetation changes. I can use this threshold to start to look at the severity of that change. So I come back here to where my fractional cover is. I'm going to comment out the fractional cover, but I'm going to add in NDVI. Remember, I said I want a threshold range of 0.4 to 1.0. I'm going to go down here, and I'm going to do the count as well. So I'm going to do threshold percentage. I'm going to get rid of fractional cover. And since this is already run a single time, I can come back up here, and I can just run this case here. Shift return runs it. And there is the result. So this result now, all the areas in red are any areas that are vegetation between 0.4 and 1.0 NDVI. And this is everything that falls within the light green or dark green of this image right here. So all this light green and dark green, and even the smallest little pieces you see here, show up in that final mask, which is what we get here. And so I can go a little further and I can run the next block. I hit shift return, and now this calculates that. What is the percent inside the threshold? 53% of the pixels in this image. It looks like it's more, but it's only 53% of the pixels in that image meet the vegetation threshold that we've defined here. So that's all for this tutorial, but I hope that gives you a good background on how to analyze spectral products.